Peter, here you're unemployed.
Yes, yes, I am recently unemployed as of today. If anyone out there has a good PhD position in theoretical physics, hit me up.
Or anything. I hear he'll just take anything at this
I'm
stage.
a bit desperate. Not really looking to be homeless anytime soon.
Right, I'm sorry to hear that. And Sam, you're not unemployed.
I have quite a stable job right now, I guess.
Right, yeah.
I'm also, my funding comes from the EU, so I guess that's quite a stable thing most of the time.
For now.
Well, we talk about, let's not go there. So yeah, I guess I'm quite comfortable with my job position.
Now, we two and other call ourselves scientists. Peter, it's all right. For today, for tonight at least, you can be a scientist.
I've lied. I've lied a lot in my life, so...
That's just being straight, right?
I genuinely would class Peter as a scientist.
Yeah.
Sure, he's not an employed scientist, but he's a scientist nonetheless.
Right. But Peter, what were you previously employed in doing?
Previously, I was working on quantum theory, specifically on cold atomic physics, so Bose-Einstein condensate kind of deal. If that makes any sense.
What is?
So, please tell us what a Bose-Einstein something condensate.
Yeah, so this is the problem that I have every time you try to explain what you're doing as a theoretical physicist. So for Bose-Einstein condensates, you start out with something cold, and you cool it down real cold, and eventually the individual particles which make up this gas, they lose their particle-like nature, and they kind of become waves, and then all these waves overlap, and you get this big, and they overlap so much that the whole thing kind of becomes one big metal wave, and it's got some really interesting fluidy, wavy-like properties, and so you can kind of observe quantum phenomena in a macroscopic regime. So you can actually see interesting interference effects and other quantum behavior in something that you can actually kind of see. So you get them up to I think the biggest ones maybe being half a millimeter kind of deal. So they're still small, but they're actually macroscopic.
Right. Macroscopic enough that you can look at them through some optics, or
yeah. So you image them using some real fancy optics. I deal with the theory, so the laser stuff.
He doesn't actually do any of it.
I see.
The laser stuff's a bit beyond me, but it is kind of possible.
Okay.
A little bit.
Okay.
It's not like it's
the best kind of science, really, kind of possible.
Yeah, right.
It's not really as practical as your stuff.
So, what is your stuff, Sam?
So. I'm a community ecologist, I guess. So,
Community is a TV show, isn't it?
Yes, it is.
So you're the ecology of that? That seems...
basically, yeah. I feel like there's probably been a fair bit of ecology on that over the years, but more generally, I look at the community of whole ecosystems. So we're looking at so it's in terms of biological organization. You kind of go from you've got all your sub-individual stuff like genes, molecules, whatever, and then you've got your organism, and then from upwards you've got populations. Well, you've got groups of organisms that interact in social groups, or some other group that isn't social for some reason. Then you've got populations of one species. Then you've got what we call communities of interacting populations. So it's communities of multiple species.
Right.
And then from there, you've got the ecosystem, which is everything, including sometimes multiple communities and whatever.
You used the word social then? Did you mean it in the way that we normally think about it?
Yeah, I did. Okay, so some animals are social, some animals are not social.
But getting back to what you studied.
So I guess so. I was talking about community ecology. So this is... community ecology is basically ecology at the level above population. So I'm not interested particularly in any one species or group. I'm interested in the whole ecosystem and how everything interacts. And so my PhD is on global change and how global change is degrading what we call ecological stability. So if you imagine your community of interacting species, and you can measure the biodiversity of that community or some other output. So biodiversity, so species contribute to what we call ecosystem functions, which is how the processes and functions of the community, of the ecosystem work. And they in turn produce these services that we as humans get from the ecosystems. So things like pollination, things like actually harvesting timber from forests. These are all services that we get.
Right.
So pollination of crops, for example, is a service that we get indirectly through pollinators
Yeah.
that are
Yeah.
in the community and doing these things.
Yeah.
And so it's important for us as ecologists to understand what these, how these communities are functioning and how that relates, because ultimately it affects what we get from the ecosystems. And if our actions degrade that too much, which we think they probably are, then things can go badly downhill. It doesn't just affect the ecosystem; it feeds back onto us, and we can no longer sustain ourselves.
Yeah.
Something I think is a unique feature of the place we currently study. Well, some of us.
I'm here for the next couple of days.
Yeah,
We don't study here.
But I mean, I suppose universities generally are a place where people from very different fields can come together and think about their topics in kind of an interdisciplinary manner. And I'm wondering if there's any overlap that we can find between quantum physics, theoretical quantum physics, and ecology.
I mean, you were asking about Fourier transforms the other day.
I was, yeah. I mean, so I think the maths might be
The
overlap,
crossover is
right?
going to be the maths, right?
Yeah,
Because I mean, a lot of science uses maths,
Yeah.
and ecologists want to understand maths but don't, and physicists know maths.
I think that would be a perfect time for your story from Vietnam. So you walk into the restaurant.
So first of all, there's a reservation system in place, and we go downstairs and we say, we'd like to eat. This is apparently, like, according to TripAdvisor, this is like the second best restaurant in the north of Vietnam. It's like a 5-course meal. It's a proper chef. It's meant to be proper fancy, real nice.
We were like dressed in shorts and
Well,
t-shirts.
yeah, we were like
shitty tourist clothes.
Pretty bad tourist clothes.
And how much was this going to cost?
So Vietnam's pretty cheap. So the whole thing for 5 courses would be less than $20.
Wow.
Yeah, it's
And it was genuinely some of the best food I've ever eaten in my life.
it's kind. I don't understand how food can be this cheap, but I mean,
Right.
it's
Yeah,
pretty
it was
great.
very
Okay,
great.
sorry, but you're
Anyway.
in the restaurant.
Yeah, so we like go up to the lady out the front, and she said, "Oh, do you want to come in?" And we were like, "Yes, please." So, do you have a reservation? And we immediately went, "Oh no, we don't. Oh, sorry." And she's like, "Okay, that's fine." And then she walked us through the restaurant upstairs to what was arguably the nicest seat in the whole place.
It's pretty beautiful.
Removed the reserved note, which was definitely for an actual like loving couple. Maybe someone was going to propose. I don't know.
Yeah.
She removed that, and then we
Okay.
just sat there. It was fine, apart from that
great.
one rat.
Yeah, it was a rat, but I mean that's another story.
That was fine. That was later on. And yeah, we sat there, and we were white and speaking English.
Yeah,
and there
yeah.
was a couple next to us who were like not elderly. They were probably
Middle-aged? Yeah,
they were
yeah.
like also white and speaking English.
With a
And
bit of an accent.
With a bit of an accent that sounded a little bit like Peter's accent.
It's because they were also from the great nation of New Zealand, it turned out.
Yeah. And yeah, I guess after a while, they, being those kind of people, just decided to talk to us.
Yeah,
So
yeah.
they did.
They enjoyed photographing our food. It was
Oh yeah, they
it
did.
was kind of weird, but I mean, I can respect that.
So she said the lady said that she didn't take a photograph of hers before she ate it. So when Peter's arrived,
Yeah, she's
she
like,
said, "Can I take a
I'm like,
photograph
I
of
guess
yours?"
so.
And you were like, "Yeah."
I mean, like, it'd be weird to say no.
Yeah.
Right. And at this point, you must realize that they were from your country.
Yeah, yeah.
New
We
Zealand?
talked a little bit. They mentioned they're from New Zealand because
Yeah,
I might have
yeah.
guessed Australia first, so maybe a bit shameful.
Yeah. So I think first of all, yeah, they asked us where we were from. You said New Zealand. They got excited. I said England. They didn't really make any comments.
Yeah.
And then, but I had to clarify. They were like, "Oh, so they were like, oh, you've come a pretty long way." And I was
Yeah,
like,
yeah.
"Oh, actually, no. Because we've been working in Japan. We've come from Japan." And this is where I refer to us as scientists.
Yeah,
and
which
Peter
was
got
like-
a bit uncomfortable.
I was like, "Oh, that's a big title," but I mean, I'll take it for now.
Yeah. And so then it led on that, of course, they asked us, "Oh, scientists, that's quite a vague term.
It sounds quite
Like,
fancy also.
Sounds quite fancy. What do you do?"
Yeah.
And then, did you go first or no, I went first.
Yeah, you
didn't
went
I?
first. You did, yeah.
So I said, I'm an ecologist. I'm interested in global change and whole ecosystems and what that means. And the guy, the man said, "Oh, that's really interesting, really important." And the lady also made some like approving noises. And then you said what you did, right?
Yeah, I think I said, like, oh yeah, like you finished saying what you were like,
Yep.
ecology, global change, etc. I'm like, oh yeah, I do physics. I think I just said I do physics.
Yeah,
I'm not sure if I really like went deep into what I do,
I
because
think
usually that's
true,
a
yeah, usually
20-minute boring spiel. Maybe we'll get into it later. But yeah, I finished, and they seem to be pretty impressed. They're like, oh, physics, oh, very, very
Yeah,
impressive. Oh.
And then I think was it immediately that point when the lady went, something about real science. Or something.
Yeah. Someone definitely mentioned the word real science.
Real
which
science, and I was like,
I can get behind that, to be honest.
Yeah, I mean, fair. So, I mean, you know, I'm not a bitter guy. I like to laugh along. I mean, I also am of the opinion that all science is relatively equal, because I don't understand physics in the same way that people often don't understand exactly what ecology is, or like they assume it's way simpler than it is, right? Which is fair, you know. I guess it's more relatable a lot. But anyway, so at some point, like, somebody made a slighting remark against ecology, and you know, I laughed it off. We had a good laugh.
You're probably used to it.
I'm quite used to it, to be fair. Yeah. And then this lady started. You know, we asked about.
Yeah.
They said they had. You said where you were at university.
So I went to University of Otago, down the south of New Zealand.
That's right.
And they were like, oh yeah, our daughters went there, or at least one of them.
Yeah, one of them. Yeah.
Yeah. We asked what she studied.
Yeah. So we then asked her. Yeah, we asked about this daughter, and they said. So the lady, she really took over this part of the conversation. She said, "Oh, you know, she's doing something like, was it finance or like law or something,
some non-science,
thing." And she said, and she seems really happy, and I'm glad it was a really good choice for her. She said she was doing some nonsense before, some kind of I don't know what it was. What was it? And then the guy then said, "Oh, it was ecology." And she was like, "Yeah, that's right. I don't know why she ever chose that." And I don't know whether she had like completely forgotten that I was an ecologist.
She had, right?
Like, she
bashed ecology like
she went in pretty hard against ecology at that stage. She was like, at first she was like, "Oh yeah, ecology's fine." Then she was like, "But I don't want my daughter doing it," you know. And then halfway through, the guy,
he kind of realized.
He knew what was going on. He had to be like, I mean, ecology's, you know, it's a perfectly fine science. Like, and she was like, "Yeah, but we don't want our daughter doing it," kind of thing.
Where do you think that impression comes from? Actually, Peter, where do you?
I don't know. Well, I think like physics, it's like people get the impression that it's like super hard, and you're like, oh, such a hard worker, and it's like, I know you kind of lauded as like geniuses. Oh, it's not true, but but like ecology, I think maybe because it is kind of easier to explain what you're doing, and like you can talk about it, you can be like, oh, we study animals and we study these systems, and people can kind of at least have a kind of idea of what's going on there.
Do you think that's ultimately something to do with the way we teach math or something like fundamental like that? Because maybe, you know, physics or these more mathematical kind of centric sciences kind of get glazed over.
Yeah.
Because of just not having the language to
understand. Well, yeah, because like a lot of like physics and the way a lot of people like understand the physics is just like you just do maths and you kind of understand what's happening through the maths, and then like after doing the maths for just years, you kind of get an idea and you kind of get an understanding of what's going on. But when you first see it, like you don't really understand it, and you just be like, oh, I'll do the maths and that gives me the right answer.
Right. And
so I think it does, like, it can take a while to kind of understand what's going on. And maybe there could be a better way to like teach maths, or kind of there might be a better way to teach the physics to give the understanding first and then teach with the maths second.
Yeah, the intuition first.
Yeah. But often it's quite hard to teach with intuition, because like when you go quantum, it's often like,
right.
Yeah, it's like the wave function is like that's maybe a lot of the audience might not know what the wave function is.
Right.
Sure, yeah.
But like that's like, oh, that's hard. But it's just like a mathematical, like a quantum object that we use to just describe the universe, and it's quite a nebulous concept. It's quite like you just got to play with it for like a very long time before you actually understand what's going on.
Sure.
Like the most popular interpretation of quantum theory is probably the Schrödinger, the Heisenberg interpretation. Sorry, no, sorry, Copenhagen interpretation. Okay. Sorry, they're different names. Right. But Schrödinger and Heisenberg were both like behind this, yeah. And so it's the Copenhagen interpretation, which is like basically has been like described as shut up and calculate, which is saying like we don't really understand what's going on, but if we just do this maths, it gives us the right answer. And that might be a kind of unhelpful way to understand what's going on, right? Because it's just be like, oh, we can't really understand what's going on. The wave function's real weird, quantum's weird, but it gives us the right answer if we do the maths. And that's there's probably better ways to think about it.
What's the weirdest thing in ecology, Sam?
The weirdest thing?
Yeah. I mean, the most difficult thing to grasp, the most unintuitive concept that I've come across. I mean, presumably, like as Peter is saying, you know, there are things that initially seem really perplexing and really difficult.
Right.
I think, you know, in my field of neuroscience, there's some really odd kind of sort of unexpected ways that evolution has sort of crafted our nervous system to be just really dumb. Like one of my favorite examples is the laryngeal nerve, which you probably know goes, you know, from your head down around the aortic valve around your heart, and then goes all the way back up to your larynx. No need for it to go down there, but in fishes, it was a direct path, and then through evolution, it slowly sort of pulled those things apart. And in the giraffe, it goes all the way from the head, all the way down the neck, around the heart, and then back up again.
Gee, that seems unnecessary. Yeah.
It is, but that's evolution for you. So what about ecology? There's some things that are just seem weird.
I mean, I'm a very specific type of ecologist, I guess. You know, community ecology, a lot of it is about understanding interactions and kind of systems. So a lot of it, some of it's kind of mathsy, some of it's kind of physicsy. Most of it's just a bit statistical. So there's not really so many unusual things, because we just try to describe observed patterns with like statistics and maths. And sometimes if you can't, you just assume you're wrong. So I mean, maybe there's things that just maybe aren't super easy to explain, but we don't really have a way to say that, because if we can't show it, if we can't like describe it statistically or mathematically, we tend to not publish it.
Right.
Yeah.
So because then we don't like have a result or whatever. But I guess some of the most like, I don't know about unusual, but some of the most interesting things is watching debates unfold. So I'm a big fan of watching like scientific debates generally in the literature. So if you see, for those maybe listening who don't read scientific literature, we publish these papers, and then often if you publish about something and somebody disagrees with you, they will publish a counter response, and then you can counter respond to that, and so on.
Right. But I mean, you know, for some of our viewers, they might be thinking, hey, you know, science, it's either true or it's not. There's no in between. So what do you mean that people can disagree in the literature? Because
a lot of science, you have your data, and your data are collected with, I mean, so not all fields use data. So theoretical stuff you don't need data. You're talking about theory, or you're modeling things, you're simulating things.
But in a way, you're sort of relying on others' data, right?
A lot of physics, I think, is physics and pure math are a bit like theoretical physics and pure math are often a bit of a separate case, because you do often just start with like an equation and then you just play with the equation. Okay. But you can use data and stuff, and there is like theoretical data stuff going on. Right. But
there are arguments, I'm sure, that we'll get to.
So there's some error associated with data collection always. But then you use that data to test hypotheses. So you form an idea, and that idea ultimately should have a testable yes or no answer. It should be either you have proven the hypothesis to be correct in this case or incorrect in this case. And that is the key part. I think that if I had to drill in one thing to anybody who wanted to be an ecologist in the world, is in this case. So
well, not just an ecologist, right? A scientist.
Yeah, that seems science.
I mean, I would say science in general. Yeah. But for us, context dependency is something that is like very, very important in ecology
than it might be in another field.
I would say arguably yes. So one ecosystem inevitably differs from another ecosystem in more ways than we can imagine. Yeah. Usually more ways than we can quantify. Yeah. And so there's a lot of this context dependency. So a lot of people, some things in the literature evolve that some ideas happen, people test it, sometimes they find it's true, sometimes they find it's not true, so on. But some of it is just that hypotheses themselves can be quite debatable.
So what about in theoretical physics? What are some of the debates, or, you know, if it's not about interpretation of data, what is it about?
What do you mean, like debates between?
Well, within the field.
Just something where somebody said something and then somebody's countered that. What might be the situation in that case?
Oh, well, often like, I mean, it doesn't happen that often. Like, and when it does happen, it's like quite a big deal, because you're like, wow, this person either did their maths wrong, or like, there's like I mean, that happens that's not super common. Okay. But often, like, it's probably mainly common in, like, in experiments.
Okay.
Like, and often, like, you can do the experiment and it shows something crazy, and you're like, whoa, and then that's where that starts a whole debate where, like,
what's happening?
Yeah, what's happening in this experiment? Because there's a thing that does happen in physics, which is often a little bit bad, which is if you do an experiment and it doesn't agree with the theory, you do the experiment again.
Yeah.
Oh.
And like this is because the standard model of quantum theory is like the best theory there is. There hasn't been anything like to test it, like to prove it wrong yet.
What do you mean by the best?
I mean, I'm imagining that he's got like a ranking system.
Yeah.
Like this is slightly above all the other theories.
Yeah, so it's like quantum theory, and then all the way down here is theoretical ecology. It's like just at the top.
Yeah.
Gotcha.
But like,
I mean, I think that New Zealand woman would agree with you. To be fair.
Yeah.
But like quantum theory, like it's really good, and like it fits the data like so well. There hasn't been experiments that have like disagree with it, and so.
Right.
Yeah,
But is that not because people who disagree with it are redoing their experiments?
Yeah.
But like, often when they do redo the experiment, they actually realize they did something wrong.
Okay.
Yeah, like it's not the classic like, we'll keep doing the experiment, we'll ignore the data
Fudge
that
the data,
disagrees.
yeah.
I mean, there have been like examples like when you fudge the data, or just when like if you do an experiment and it like happens to just like give like a significant result or a result that seems like correct and significant, and then it turns out just by chance that it's incorrect.
So some of this is kind of what you were saying about when you get data, and some of the disagreements can be just about how you interpret the experimental results, right?
Yeah.
So some of it is not necessarily about the concept itself, but it's about the interpretation of results.
Yeah.
So somebody will publish something saying, we found this, we think it means this.
Right.
And then often the reply is just, actually, we don't think it means, we other people don't think it means that, we think it means this other thing.
Yeah.
I think that one of the big examples, I'm not sure how recently this was, but they thought they found a pentaquark particle, which is most particles that were found are either made of 2 or 3 quarks.
Okay.
I see.
I think that's
like,
5?
Yeah, and so pentaquark would be 5, and they'd be like, whoa, that like actually like revolutionizes just how we just think about particle physics. And like they thought it was great, blah blah, and it was a big deal, and then it turned out that it was just a statistical anomaly. Like it
happens.
Yeah, I mean that happens in science. Like it's not their fault, but like sometimes,
Right.
Did they retract the paper?
Yeah, like that's.
Oh wow.
Like I think things like they're probably pretty sad about it.
Yeah.
I don't actually know like the specifics.
Right.
But yeah.
Peter, you finished your undergraduate recently, right?
Yes, yeah, I have.
So you're probably the closest to this change. What's the big difference between say classes and research?
What is different? I don't know. It's kind of in physics. It's really interesting because you spend like your whole undergrad just being like taught stuff and like kind of accepting the word of your lecturer, and you'll be like, well, what he's saying is the definition of truth,
right.
And we'll just like keep doing this. And then it's really interesting, like going forward, doing research and kind of working stuff out for yourself, because it's the first time like everything else for undergrad, like most of the stuff you're doing was worked out like before the 60s. Like physics is like a pretty like most of the physics you learn in undergrad is very old, and you have to get pretty far up in a specific field to get up to science that you're doing like that's been worked out in your lifetime.
Right.
Like it's someone like around our ages.
Yeah.
And so like the biggest difference like is kind of doing research and kind of like working on new stuff and stuff that like isn't just like already known. It's like you actually get to do something new, which is pretty exciting.
Yeah.
And from what you recall, Sam, what's the biggest difference coming from undergrad to grad?
From undergrad to beyond.
Yeah.
I guess it's freedom and the ability to and need to think for yourself.
Yeah.
So it's basically exactly what you just said. Like it's a difference between, although sometimes at undergrad you're not necessarily being spoon-fed, but you're certainly being led down a different direction. But when you are embarking on a research project and you have an idea, and sure you have an advisor or someone more senior than you to help you with this idea, and they have some ideas about how they think it should be done.
Right.
You're the one doing the work, and you're making I don't want to say like analogous to like people on the ground making hard decisions in high tense situations or whatever. But like it's basically that you're making the day-to-day decisions which affect all your science from that point onwards, right? And if you find later that you made a terrible decision on day number 1, you're going to have to go back. And so that's a lot of it. Yeah, a lot of it is like trial and error. And like actually one of the big differences, I guess, is making loads of mistakes.
Right.
And just doing a lot of pointless things.
Yeah.
Like, I do so many pointless things. I do something, and then a week later, I'm like, wow, I spent a whole 2 days working on that, and now I don't need it, and I'll never use it.
Yeah. I mean, I code all day, and
Yeah, me too.
I think, okay, so we all share that, and I think anyone out there who codes will know it's just a case of like, find the most frivolous, annoying bug and kill it. And then maybe, you know, that's 90 to 80% of your work. And then the 10 to 20 is like, oh, it all worked. And finally I can actually do some science stuff, you know?
Yeah.
And I find writing the same as well.
Right.
When you get to the end of your project and you're ready to write up as a manuscript to submit to a journal to become a paper, you write it up. You probably don't like your first draft, so you write it a second time. You probably don't like that draft. Maybe you go back to your first draft then. And so that kind of happens a few times. Then inevitably you submit to the journal, get rejected. And then the reviewers say, oh no, we don't like it this way. We think you should do this instead.
Right.
Actually, one of my favorite comments from a reviewer is always, oh, this isn't the experiment I would have done.
Right.
Which is like, ooh, I mean, it's not really the experiment we were doing. So anyway.
Right. What's your experience with all that, Peter?
Oh, well, my experience is pretty minimal. I've only just finished undergrad, so I haven't published any papers yet.
Yeah.
I'm currently working on a paper, which I've been procrastinating for a very long time.
Yeah, he says he's been working on this paper.
So,
I've seen it.
I haven't really been working on this
His
paper.
intro says, please write intro.
But surely, like, when you write a paper, the intro, the conclusion, and the abstract, they're the last bits?
Yeah, they are.
Yeah, like, I've written, like, mock
So
papers.
what parts are left?
You've got to write, like, all the kind of the meat, right? The real...
Parts of it.
Methods and results.
all the results, like the bits that actually...
Do you have results?
Yeah.
As a theoretical, what would so you're like, you do some maths to prove a concept, and then you
What are the
your
headings
results
in
are what are your
Oh, well, so how this is probably pretty specific because
Sure.
for this project I was working using a theory and like an equation that my supervisor had come up with, which is a way of describing Bose-Einstein condensates. Because normally
a good Bose-Einstein
condensate.
It has the word Stein in it.
As in, like,
Bose
the drinking strain?
and Einstein.
Oh, okay.
Two pretty famous physicists.
Okay.
Yeah, but Stein, I was thinking like...
I was imagining like the huge Steiner beer. Like,
It's not quite.
Chug, chug.
It's not quite that exciting.
Please continue.
yeah, please, sorry.
So normally when you describe Bose-Einstein condensates, you describe them at 0 temperature, like 0 Kelvin, which is like a bit dodgy.
Why is it dodgy?
Well, that's physically an impossible temperature to reach.
Okay.
Like, theoretically, we can make Bose-Einstein condensates, and this is an impossible temperature for anyone to really imagine, but you make them between like 50 and 100 nanokelvin. So it's very, very, very cold.
Yeah.
That sounds quite cold.
It's super cold, but like, there's obviously still some thermal energy in the system. It's still like...
Sounds like an English summer, am I right?
yeah.
Hey,
I mean, you die very quickly.
I die very quickly.
But yeah, so this...
So the fact that there's any thermal energy in the system...
And so that kind of introduces like thermal noise, kind of. And it means that some of the particles in the Bose-Einstein condensate aren't like in this weird wave, and they're kind of just like... They're not properly, we call it coherent. And so they're kind of causing some weird thermal effects. And so normal BEC theory, like they just do 0 temperature and they ignore all that.
Right.
And for most things, that's actually that is shockingly good. Like initially, some guys, Gross and Pierre-Vesky, came up with this equation back in the 50s or something. And they came up with this equation, they thought it was like a toy model. They're like, oh yeah, this is a fun thing to play with.
Right.
But it definitely won't be anywhere near good enough to describe the real world. And then it turns out it's almost perfect.
Wow.
And they're like, oh, well, that's pretty sweet. But like there is still some thermal effects.
I see.
And so this theory is working on like, my supervisor came up with was like the thermal effects on Bose-Einstein condensates. So for my thing, I was looking at a specific case of this.
Okay.
Are you allowed to talk about this just for the record?
Yeah, I mean, I've got my thesis.
Oh, okay.
Yeah.
Just checking.
Yeah, and so I don't think it's super super controversial or confidential. And so the chapters of the paper that I will eventually write are going to be it's going to be like you've got your intro, you've got then like a chapter kind of describing just this
a chapter?
Not chapter, a heading,
A heading?
a section like describing just this theory, and then I've got in my stuff I did some analytical work, so I just like literally started with this equation and then did some maths and came out with an answer.
normally, from an experimentalist point of view, analytical would mean you analyze something. So what are you analyzing?
That's crazy.
Yeah.
Oh, wow.
Analyze some data, I mean.
Yeah, because how in theoretical physics, things are described as analytics, which is and taking an analytical approach, which is like doing maths on paper, as opposed to numerical, which is letting a computer do it for you and just running computer simulations.
I see.
Yeah.
And so doing it analytically, i.e. kind of with equations, paper and pen style.
Yeah.
Is that correct?
Yeah, that's exactly. I just wrote out this equation. It's been a long time writing it, just doing maths.
Yeah.
And hoping that it works.
Yeah. But presumably that's. Does that have? I mean, it feels more formal.
It has more form, but also it gives you like a kind of a better understanding because you can actually at the end you've got like an equation and you can look at the terms in the equation and see what affects what.
Right.
Well, if you do this numerically, it's often a bit harder.
Okay.
Because you can't like as easily like see like this term here in this equation affects this.
Yeah.
Like numerically because you just get your numerical results.
Right. I mean, you're literally building a model. So yeah. I'm actually really into music. I really like jazz, and I kind of think that there's something similar between music fundamentally and science. It's creative, and at the same time, it's kind of, it's got some order.
Yeah, it's quite structured and ordered.
Right.
Yeah.
But there's like a lot of room for creativity in there, especially in something like jazz, which is my favorite sort of music to play and to listen to. What do you guys think about that? And are there any other things like, that are analogous to science in kind of a weird way, or a special way?
I guess in the way that you've just described, music surely at its heart is a lot of it is about maths, right? Because you've got your beats and everything has to be in order, and then there's logic about which notes sound good together, and that's all to do with the harmonies, and that's all basically determined by mathematical changes in tone sequences and things like that. So I guess a lot of that comes back to maths. I don't want to bring everything back to maths. I seem to be bringing everything back to maths. It's the language
of the universe, really.
Yeah, effectively, yes.
People often the fact that I heard as a kid all the time, I'm not sure if it's true, is that music and maths use the same part of your brain. But is that a neuroscientist? I'm not sure about the validity.
I'm not so sure. I mean, actually, I did my undergrad thesis, my honors thesis, which is for people outside of that system. It's where you do undergrad sort of taught, and then you do a 1-year research degree, which is the honors part. And
it's not how it works in the UK, but
that's how it works in Australia
and New Zealand.
And for you guys,
New Zealand. So I did a little thesis on sort of human perception of non-linguistic sounds, and of course one type of category of non-linguistic sound, I should say, is music. And it is quite interesting what people... I got, participants to rate, how pleasant a sound was, how complex they thought it was, and stuff like this. Some interesting stuff came out of that. You can read the preprint on BioArchive, and, it's under review somewhere.
Yeah. No detail.
It was already rejected once, but somewhere else.
I know that.
Yeah. Anyway, but I mean, for me, what's interesting though about what you guys have just said is music is kind of and to answer your question, it's kind of music uses the whole brain basically.
Yeah.
It's kind of all these fMRI studies. I'm sorry to bag on the fMRI study people, but some of them are kind of bullshit.
To be honest, most things I hear about neuroscience and psychology, I'm always but is it really?
But have you heard that we only use 10% of our brain? But I mean, getting back to this music thing though, I was thinking it's kind of just seems unreasonably beautiful. Why is it that something just so happens to have, some kind of structure or some kind of harmony? Why is that beautiful, and then one note away, it's not?
Well, I think a lot of it is cultural, right? Because I think when you listen to music from other, I know rhythm is pretty that's pretty across a lot of cultures. But if you listen to music with a different scale, it can be a bit jarring. When you listen to it, especially for the first few times.
That's true.
The first time I listened to Chinese music or something that uses a non-Western scale, it does sound pretty weird.
That's true. Yeah. But still, somehow there are as you say, fundamental things say rhythm or something.
Yeah.
That are beautiful. And I mean, I wonder if there are other things like that, I don't know, you know, I mean, science can have its own sort of beauty, but like kind of logical things, or paintings, or
I mean, music, presumably, some of the reasons we find like certain rhythms and certain patterns in music particularly attractive, presumably some of that comes from nature, right? So for long before we were building cities, we were, you know, just a part of the ecosystem naturally, and so we were relying on sound as one of our, you know, hearing as one of our important senses to help us do everything, including hunting for food and everything like this, you know, gathering food and whatever. And so I guess, probably a lot of how I guess modern music has evolved has been through our depiction and our understanding of what the natural world sounds like. And so I would guess, you know, we find birdsong pleasant a lot of the time. Unless, I mean, there are a lot of birds out there that are not so pleasant.
We find some birdsong.
A lyrebird imitating a jackhammer is not that pleasant. But actually, in my project, I found, say, you know, nature sounds, waterfalls, things like this. Trees, you know, swinging. Not that they have much sound, but you know, the creek.
The
sound.
creaking.
That people all rated those as pleasant. In my study.
So, I guess so. I've got a little bit of experience in this. We did a.
Sam continued to talk about birds for a good 15 minutes, but he also had this to say about a particularly annoying rooster.
And this machine learning approach just couldn't separate crows from roosters. So my biggest hatred for several weeks was this rooster at this one field site.
Yes.
I considered going and manually removing the problem at one stage.
We don't condone that, of course.
We'll edit that out maybe. But that's science. So anyway, I have accidentally just derailed this for about a very long time.
I'm curious because like it's one of the things like machine learning is one of like the big buzzwords in science and everything these days. And I'm sure that's a lot of the stuff you do, a fair bit of it.
Well, yeah, I mean, I just finished 4 months of that, and it sounds like I'm about to do another 4 months, actually.
Oh, fun stuff. But like the things I've heard about machine learning is that it is kind of hard to tell often why it doesn't work. Like it'll give you an answer, but like it's hard to actually get like a deeper understanding from it.
Yeah, I agree with that sentiment. It's interesting though that you say that because something that I'm interested in is kind of debugging that and exploring that. I mean, there was a paper actually, an opinion in Nature or Science just last week saying, you know, the magic of machine learning is all but erased. It's still there and really prevalent. I actually, I had thought about writing some response. I can't really do it in such a journal, but you know, I think actually there's a lot of people now thinking about, you know, why and how those things are working. I mean, it's just ultimately it's just lots of matrix
multiplication. It is just maths, right?
Yeah, it's just math. But yeah, I mean, it's ultimately these things. You know, especially the sort of dynamical ones like recurrent neural networks, which have connections in on themselves. So you know, you take some input to this network. It has some math happening, and some of that math gives some result, some prediction. But then also some of that math stays within itself and it continues to have activity. That's the recurrency element. Normally, say, you know, they're all kind of all the connections are going, all the math, is kind of going in one direction or the other. But with the current neural network, it sort of has this internal activity, and in that case, you're actually studying a dynamical system, you know, and then you can apply, you know, a lot of the same kind of systems, kind of investigations as you would do in even, you know, as far as ecology goes, or you know, in some sort of physical system. So those cases, I think, are actually quite nice. They're quite approachable from other traditional science.
Okay. So it isn't just like a kind of obtruse black box kind of thing. You actually can kind of see how the sausage is made inside this.
Yeah, but how you should is a big question, actually. Because a lot of people in my opinion, have sort of taken, as you say, kind of the buzzword of machine learning.
It's a big one.
And just ran with it, and they've got amazing results, but they have no idea how they got there. I mean, they have some intuition, and we have general, if you add more, if you have a bigger network, it's going to be better.
Yeah.
Well, okay.
Maybe.
If you have more layers, or if you have, if you go that way or this way, it's going to be better. But there's a lot of other complexities that you can have which make it better or worse. Like, for example, in your case of training bird songs or bird calls, maybe the spectrogram isn't actually the best input to be using. Maybe there should be, some waveform input or some sort of transformation done. Maybe this whole model should only look at a few different frequencies, as examples. But that's, that's something that our brains do kind of already, right? We through experience filter out this unnecessary information and pay attention to particular features.
Yeah, I mean, like that's one of the reasons humans are so successful. Like, because we've just spent millions of years being trained to be good at these specific things.
Yeah. I mean, another fascinating thing about humans is this one-shot learning. So machine learning, you have to give it
That's true.
so many examples. But, if I teach you, I don't know, some kind of gesture, you can immediately do that gesture based on your understanding of your just...
It's your body and
yourself,
your body.
your
And
steer once, and you kind of, when you learn, you kind of be like, oh, I'm learning this thing.
It's imitation learning, really.
Yeah.
Yeah.
Because computers can't imitate. I mean, I'm maybe making a broad claim there, but
well, actually,
I guess I would assume they can't they can't learn through imitation. Maybe I don't really know.
Actually, I suppose I shouldn't have said that. Really, it's a bad example because even in my most recent work, I made a robot arm.
Yeah, I guess that's kind of what programming is, right?
You just go in any way along a plane. Like by teaching, by just saying these points, and you could. It's just interpolating between all those points, right?
Yeah.
Can we just take a second to appreciate that he did just say he made a robot arm?
I didn't.
That's the most sci-fi thing I've heard today.
I didn't make a robot arm.
You're just programming a robot arm.
It's still pretty
a
cool.
robot arm, right?
It was a pretty massive robot arm too, way bigger than my arm.
Were you ever scared it would go crazy and kind of eat you?
No, actually, there was no. I think we took the little gripper thing off it because that thing is kind of dangerous.
Bash you
so
to death.
the likelihood of if it became sentient and went on a rampage, we're okay, are we?
Yeah, but
Can it climb
it's
stairs?
also fixed. It's like this microphone stand.
Okay, right.
It can't really.
Yeah, okay.
I mean, I don't know, but octopuses can do some weird things, and they don't even have legs or anything.
I mean, they've got eight
of them.
No, but they're not terrestrial animals.
No, that's true.
But I've seen them. I've seen the videos on YouTube.
That's
yeah.
Just crawl out of their tank and.
Yeah, they do all kind of weird stuff.
Yeah, but
they also predict the outcome of the World Cup normally, don't they?
I mean,
what?
Paul,
yeah.
He's dead now, but
he's dead. Yeah. R.I.P. Paul.
Rip Paulie.
Yeah.
So he was an octopus.
He was an octopus, and he used to famously predict the outcome. Huh? He lived in your hometown, Kaku.
Represent.
Tell us
No,
about
Bonn,
the octopus?
He lived in a sea life at Oberhausen.
Oberhausen.
So there was Paul the octopus, and he used to what was it? They gave him a bunch of cards, and to choose the right one.
There were just two boxes, and then he just got in a box.
Yeah, that's right. Yeah.
And then there's one of the many examples of if you have enough. If there were three
monkeys and typewriters.
Yeah, monkeys and typewriters. If maybe there were 3,000 octopuses and Paul just happened to be the one that got them all right.
Right. So how exactly does this even happen? I mean, I don't follow football at all, of any form, really.
I mean, it's just before the match. There's two teams that play against each other, right?
I understand that.
So he was
He decided that the octopus Paul had anything to do.
Probably the people at the zoo who wanted to make some money. I assume probably worked quite nicely.
Yeah, Paul's pretty famous for his time.
Yeah.
Well, yeah, clearly, yeah.
Until he died.
He died. Rip Paul.
R.I.P.
Never forget.
Sweet Paul.
Never forget.
Oh, mate, gone too soon.
Yeah. So, okay, so, yeah, I don't know where to go from here.
I mean, I feel like we've reached peak. We've peaked now. This is it.
Yeah.
Paul, the World Cup predicting octopus is the pinnacle of this podcast.
Yeah,
Absolutely.
We had a good run.
This has been significantly scientific.
Yeah.
Especially at the end.
Yeah. Any final thoughts?
Oh, well, I've got the old theoretical physics professors out there who are wanting a top-notch student.
Can we not forget for several minutes that you're unemployed? Come on.